Hello, quantum mechanics will be discussed today in this video lecture. So this lecture is divided in 4 parts. In the first part, quantum mechanics will get an introduction starting from very start of the science or the physics. In the second part, the elementary principles governing the quantum mechanics will be explained. Third part will introduce the postulates of quantum mechanics. And in the fourth part, few applications based on quantum mechanics will be discussed for deeper understanding of quantum mechanics. Let us start with first part, the introduction. The journey of physics up to quantum mechanics today started with the beginning of thinking of science in the old era. The thinking of a right way of doing anything is philosophy. The philosophy is the mother or father of every science of present era. The mechanics is the integral part of philosophy of physical objects or physics. In this way, to resolve the problems of objects that were visible to eyes, classical or Newtonian mechanics was developed. Being the foundation of quantum mechanics, classical mechanics finds the importance in discussion of quantum mechanics. It is worth mentioning that at the end of 19th century, the physics was essentially classical mechanics. The Newtonian mechanics was supposed to resolve almost all the problems of known systems until the systems of microscopic dimensions were discovered. Therefore, one can say that the old era was the era of beginning of scientific thinking. On the other hand, in the modern era, we are in stage of formulating the science or model the science. The example is quantum mechanics. Quantum mechanics is applicable to all the systems of any dimension, even on the ghosts, means systems which are invisible to our eyes. The transition from old era of classical physics to the modern era of quantum physics is the era of elementary quantum mechanics. So, the basis of Newtonian mechanics was philosophical. In this, there were two types of entities, the particle or wave. Both these entities are entirely different, where the particle is an object visible to eyes and wave is a disturbance in the particles of the mediums. A particle has some properties named as observables, and the state of particle is defined by its position in space and momentum. The Newtonian mechanics relies on some equations of motion of the system, and these equations of motion are able to predict exact position and momentum of the particle. The laws of motion can be written in terms of particle trajectories. On the other hand, the quantum mechanics is probabilistic approach to solve any problem. In this, the concepts of wave and the particle are left behind, and the dual nature of matter and wave is believed to exist. What I wish to say to distinguish quantum mechanics from classical mechanics is that the quantum mechanics relies on Schrödinger equation to be the equation of motion.
In quantum mechanics, we solve Schrödinger equation to reach a meaningful endpoint.
The laws in quantum mechanics are based on various principles like wave-particle duality and uncertainty principle, and it holds good in microscopic systems, that are the systems which are invisible to our eyes. The observables in case of classical mechanics are replaced by operators in quantum mechanics. So, up to now, we have concluded that classical mechanics and quantum mechanics describe two regimes of dimensions of systems which are respectively macroscopic and microscopic regions. Next, let us see what forced the mankind to discover method of problem solving other than the classical mechanics. These can be called the crises in classical physics that demanded quantum mechanics to be formulated. The first crisis was the question, why don't the atoms disintegrate? It is because if the electron is orbiting around the nucleus, then it is in acceleration. Because the velocity of electron in motion in circular or elliptical path is changing at every point of path, and the accelerating charge radiates its energy. As the energy of electron will decrease, it will come closer to the nucleus and finally fall in the nucleus. And the classical mechanics is answerless. The other problem with the classical physics was the photoelectric effect. I hope you are familiar with the photoelectric effect. If not, I recommend you to read introduction of any book on quantum mechanics. To start with, take potassium surface and shine it with light of different wavelengths. You will notice if you are using red light, no photoelectron will be ejected from the potassium surface, no matter how bright or intense the light is. But if it is shined by green or blue light, the modest intensities of light also are capable of knocking out the electron from the surface. This behavior cannot be explained by classical mechanics, where light is a wave. Because more intense light means more energetic light wave irrespective of its frequency. So, the ejection of electrons from metal surface must be the function of intensity of light rather than its frequency in classical mechanics. But the reality is reversed. The photocurrent is a function of frequency of the incident light. Note that Einstein explained it, leading him to Nobel Prize, and he coined term quanta of light or the photon, which became the foundation pillar of quantum mechanics. However, he was not fully convinced with it. Let us talk about one more crisis in classical mechanics, and it is the discrete spectra of atoms, which is the signature of each atom. Classically, the discreteness of atomic spectra is not possible, and this was the another hit on the classical mechanics. It is enough with the crisis. Let us now talk about the beauty of quantum mechanics. I wish to start with what we could miss if some great minds would not have developed quantum mechanics. Without quantum mechanics, we could never have semiconductor devices, computers, cell phones, lasers, CD or DVD players, barcode scanners, surgical applications, MRI, nuclear reactors, and atomic clocks or GPS navigations. But the physicists could not digest the quantum mechanics so easily because it was so novel and weird. Weird? By weird theory. Once in a lecture, George Gamow said that anyone at present in this room has a finite chance of leaving it without opening the door, and of course, without being thrown out of the window. This was based on implication of quantum mechanics, named as tunneling. According to tunneling, a particle can cross a barrier even if it has lesser energy than what it requires to go through. So, is it a weird theory? It is good to leave the decision on your wisdom.